Alô? Paulinho, pode começar, Paulinho. Welcome, everybody. Good afternoon. So we'll continue our workshop, and it's a pleasure to have here Professor Michael Correa. Michael is a good friend, and he was from Unicamp, but now he's located at the IME USP. So it's our brother Uspiano. Very good. And Michael has a strong formation in finite element methods and for different problems, and he's going to talk about some coupling strategies for black oil in pore-elastic media. So Michael, it's a pleasure to have you here, and thank you for coming, and the floor is yours. Thank you.
Thank you, Fabricio. Good afternoon. Actually, the pleasure is all mine. And before starting the talk, I want to refresh something. I don't know if Poti remember that, but we first met, at least officially met, there at CNMAC 2017 in Florianópolis. Do you remember that, Poti? There was a kind of prize from SBMAC for the best thesis, and he was there with his student, Igor Prata Soares, presenting a pretty nice work. They were remeshing things. And I was really impressed because one of the examples, they put a surface mesh in ants. So these guys were remeshing ants. And at that time, all my work, my PhD, I was there also, my PhD was in stabilized finite elements. And I only used orthogonal meshes. I was not worried about anything far from a square domain. And I saw that and I thought, oh, these guys, they are really serious. This is amazing. So it was my first impression of his work, and I was not wrong. So I just wanted to remember that, but it was probably our first official introduction. So here, in this talk, everything that I'm gonna present here, several topics, they were developed within the CPID-CMI. So again, I need to thank you, Poti, for the invitation to be part of the CPID-CMI. It was an amazing experience. And I'm gonna use this opportunity here to share some ideas with Poti, because we haven't met for a while. We don't have our weekly meetings anymore. So I'm gonna use this time to share some ideas with him, and also Hugo and everyone in the audience. So the first topic is related to the modeling of black oil. That's a problem related to porous media flow and oil industry. And this is a disclaimer here. All the simulations in this talk were performed on orthogonal mesh. So I didn't change that much with the time. So still using orthogonal meshes, at least when I can. So sequential formulations. The full research of this part of sequential formulations can be found in this paper that was in collaboration with my colleague Massimo Muradi. Massimo Muradi is a specialist in porous media flow. I don't know if you know him. He's from LNCC. And he has a long story of collaboration with oil industry, lots of nice projects. And he brought this really nice problem, a challenging problem. And we did this collaboration for years before we could finish this paper. It's a pretty interesting paper. And the idea here is when you have a coupled multi-physics problem, like this one, this is an illustration of a section of the Brazilian pre-salt. And in the end, you want to extract oil from this colorful part of the domain, that's the reservoir, but we also need to solve, for example, the geomechanical coupling with all the surrounding rocks. Here we have the overburden, the underburden, side burden, all these surrounding rocks. So if you extract oil, you are going to change the equilibrium locally and transmit to the rocks, and you need to solve the problem for the mechanical response of the rocks. So we have here in this nice problem, yes, you can see here. For example, sub-problems. We can think about sub-problems. The reservoir, that's a compressible porous medium. The geomechanics of the surrounding rocks may be different kind of rocks. And when we have this kind of problem, we have the option of solving everything monolithically, everything coupled, or to introduce some sequential formulations where we solve the problems sequentially. So, for example, focusing only on the reservoir, we have here bounded conditions for the flow, the hydrodynamics, bounded conditions for poromechanics, and we can solve the problem iteratively. And for the black oil model, it's not working that well because I'm pointing to the TV. I shouldn't point to the TV. I should point here. And these are some basic hypotheses for the problem. So we have three phases: oil, gas, and water. And we also have three pseudo components, also water, oil, and gas. But in the black oil model, you can have the gas component dissolved in the oil phase. So this is the difference. And you can, depending on the relation of the pressure, you can release gas from the oil, and then you have more gas going to the gas phase. And if you increase the pressure, this gas gets trapped inside the oil, and you have no more the gas phase. So this is the particular behavior of this model. So for the flow, we can state the equations using saturations and velocities, or using concentrations. First, I'm going to show you here the equations, the mass balance equations for the formulation in terms of saturations. So we have here the mass balance of the water component, oil component, and the gas component. Here, S are the saturations, and they are restricted to these volumetric restriction constraints that the sum of the saturations is 1, okay? And here we have the formation volume factor, the B functions, and we also have this R function here is the dissolved oil gas ratio, and the V are the Darcy velocities. Okay, we can state the problem in terms of the saturations, but we have one major problem here. Here is just showing how we write the Darcy velocities. Here we don't have the pressure, capillary pressure, so we only have one global pressure. But the problem is that this equation 1C, when we increase the pressure and the gas phase is no more a gas phase, you don't have the gas phase anymore because all the gas was trapped in the oil phase, you don't have this equation anymore. So you don't have the gas phase anymore. So you start with 3 phases, and sometimes you just drop to 2 phases. So it's much better to state in terms of the concentrations. So here are the equations in terms of the concentrations, because you always have the concentration of gas. You may not have the phase, but you have gas inside the oil. So the first thing is to write the equations in terms of concentrations. And for the geomechanics here, we just assumed poroelastic media. So the porous matrix is a linear elastic solid. And we use the Tesag decomposition that we split the total stress in terms of the effective stress, that's Hooke's law here for the effective stress, and the pore pressure part. So this is pretty standard. So the novelty here is that the porous media can deform. It's not rigid anymore. And another important contribution of this model, in this paper, we have several contributions. One that I think that's the most important is the system of differential equations that I'm going to show in the next slides, because we use it here, this formulation in terms of this porosity. This is the Lagrangian porosity. So because the media is deforming, you have changing porosity with time. So the volume available for the flow is changing with time. So this is the system. We need to solve this coupled system. The blue part is the flow part. That's W is the total flux. And this is a kind of a global Darcy equation. And we have the mass balances here. And also have the geomechanical coupling. And the saturations can be post-processed after you have the concentration. So this is the system that we need to solve. And as I said, if you want to solve it monolithically, it's pretty expensive. You can use a huge Newton and solve everything coupled. It's expensive, really, really expensive. But here we are going to split the system in the subsystems for the flow, the transport, and the powder mechanics. And I'm not going to show the methods because actually you can choose the methods of your preference. We're only going to explain the idea of the algorithms for the splitting. This first algorithm is, we call it two-level sequential scheme. It's pretty hard to see here, but in this algorithm, we have two loops. The first one, we iterate inside the flow. We first, we fix the total mean stress and solve for the flux and the pressure. Then we have the flux and pressure, we keep the total mean stress fixed and update the porosity and go to the transport equations and perform the transport. And we iterate between flow and transport till converges. When this inner loop converges, we go there and update the total stress. We solve the geomechanics. So here in this algorithm, we only solve the geomechanics after converging the inner loop for the flow and transport. And the second one, the second version, is different because we only have one huge loop. So here we fix the stress, solve for flux and pressure, and fix the stress. Now we have the flux and pressure. We updated, solve for the transport. And with the transport, flux, pressure updated, we now solve for the geomechanics. So in each loop, in each step here, the loop, we solve the three problems. What's the difference between them? The difference is if your geomechanical problem is hard to solve, it's expensive. This algorithm is not the ideal because you need to solve the geomechanics in every step. So if you have a problem that, for example, that problem with the pre-salt, you have much more solid than actually the size of the reservoir. So you have solved a huge geomechanical problem. So this algorithm is better because you are only updating the stress after converging the flow and transport. It's not immediately that we can see that, but this is a pretty nice result. And just to show one important numerical method, this is a thought experiment there in the paper. I'm not going to detail much, but we have here a closed reservoir, closed box, and inside we have oil, gas, and water, and we kind of pressurize and depressurize this box. So we have no flux, And what happens is that depending on the pressure, we start releasing gas from the oil. So we need to set what is the bubble point pressure. If the bubble point pressure is 10 MPa, for example, we can perform all the cycle without releasing gas. If it's 15, when the pressure reaches 15, now we start releasing gas. So it's this red curve here. And this blue one is for the bubble pressure of 420. And so when you cycle, we need to guarantee that all the gas goes back to the oil. And it's not easy. We tried different strategies. And in most of them, when you go back, you start to have negative saturation for the gas. So it's a pretty hard problem to keep this positiveness of the gas saturation. And always the reviewers, one reviewer asked, oh, I can solve that using a sequential formulation, a pretty standard staggered formulation. Why don't you use just a staggered formulation? And we did that. And you can see here that if we sum the saturations, here in this orange dashed curve, we have the solution for the one level sequential formulation with 100 time steps. And the pink and blue one are for the staggered with much more time steps. And if you try to sum up the saturations, they are not one anymore. So, okay, you can do that, but you are losing or hurting the mass conservation. So this is the first problem. And there we also tried different media, heterogeneous, first order and second order versions of the method. You can find it there. So this is a pretty nice problem related to the oil industry. But as I said, I'm going to use this time to, I don't know how much time I have. Please stop when it's over. But this is a nice experiment that I want to show to Poti and also Hugo. Simplified model for a heart chamber. The motivation for this work is already published in this paper. And Professor Carlos Eduardo Maggi, he's from mechanical engineering, and his research involves the thermodynamics of the human heart. It's pretty nice research. And he asked me, Michael, I want a really simplified model for the left ventricle heart chamber. And I want to use Navier-Stokes, but I want really simplified model. So we went to the literature, and this is the most simplified possible model when the left ventricle is modeled by a rectangular domain. And we have here the aortic and mitral valve that are treated as boundary conditions for this problem. So okay, let's solve the Navier-Stokes equations here. And the idea was to mimic a cycle of the cardiac cycle. So we have here the first part of filling. So we are admitting the mitral valve is open. We are admitting blood in the chamber. And so we are increasing the volume to a point where the mitral valve closes, and we pressurize now the chamber. And you have this part here, this volumic contraction. Then the aortic valve opens, and you eject blood. Then the aortic valve closes, and you repeat the cycle. This is the idealized cycle. So, very good. Let's go there. We have the fundamental equations here, the mass balance, the linear momentum balance. We assume the blood is Newtonian fluid. And you have Navier-Stokes equations, and go there. We are ready to solve the problem, or at least to simulate. But there is a problem, huge problem here, because we assume the fluid is incompressible. So we have a fixed domain, incompressible fluid, and we are treating the valves as bounded conditions. So if we open the mitral valve and try to inject blood there, it doesn't admit blood because it's incompressible. It's only admitting blood if you can also inject and extract blood from the same valve. It's not the way the valve works. So we should modify, or at least avoid using this simplified problem. If you work with this problem some of you already knew, oh, it's not gonna work. But somehow we didn't know. So we got surprised. We shouldn't be surprised, but we got surprised because it's not gonna work. And then it was a really sad moment. But we went back there and used the concept of porous media flow, because in porous media you have the porosity. The porosity is related to porous media flow. We don't have porosity in the continuum model like the fluid model here. But I thought, okay, if we introduce a capacitance function that somehow mimics the way the porosity works in the porous media. So we created a phi function here. This function is saying some points of the domain, they can have more fluid than the others. Okay, it's mathematical, it's not physical. And the restriction is that the total volume is just the integral of this capacitance function. And if you do that, we are going to modify the Navier-Stokes equation, including all this phi function here. We don't have the divergence of the velocity is 0 anymore. We don't have incompressible Newtonian. The fluid is incompressible. The problem is the fluid is incompressible, but we are including a function that allows the volume to change. So this is the new formulation of the Navier-Stokes. We just called modified Navier-Stokes. And it's important to say this phi function is known a priori. We know it's not unknown. Okay? And if you do that, as I said, I like finite elements. Just solving using classical finite elements, the velocity pressure formulation. And if you do that, if you use Galecki, you need to be aware that in this problem, you need to choose a stable pair for the velocity and pressure. In this case, for example, these are bad choice. If you use bilinear velocity and pressure, it's not going to work. You need to stabilize. And the same for biquadratic velocity and biquadratic pressure, but a good pair is this one. It is well known as Taylor-Hood elements with biquadratic velocity. Here, but you need to be aware that if you choose discontinuous pressure, you need to take care, because if you map the pressure, the results are worse. You cannot map the pressure here. It's a technical observation. But now we are ready to try again to simulate the problem, the cardiac cycle in the left ventricle. And we just created a capacitance function here that emulates the volume changing with time. And this is the capacitance function. It's not unique. You can create different ones. This is just a simple one. I can explain later how we get this result. And it somehow allowed us to simulate the problem. And now we are able to simulate the cardiac cycle using, it's important to remember, our mesh is fixed, our domain is fixed. The fluid is incompressible. We just created a capacitance function that's simulating the volume variation of the chamber. And we could emulate here the diastole and the systole. So it seems that this simplified model works, at least for the volumetric restriction. Here are some numbers. And also, again, the reviewers, they said, okay, seems to be nice, but I'm not sure it works in 3D, but it works. You can create the same idea of the capacitance function in 3D, and you have a much different velocity profile. It's totally different from the 2D. And we were a little bit worried, but it's totally supported by the literature. When you move from the 2D experiment to a real 3D, the vortices, everything are totally different. So this is the idea. I have some nice simulations here to show. Let me check if. So this is the velocity. I don't know if that simulation of the emission and the kinetic cycle. So you have two main vortices, and the domain is just a rectangular domain. You can use all the domains, not a problem here. If you change the domain, you for sure are gonna change the profile of the vortices. And this other one here is a nice simulation that I'm just representing the capacitance function. I'm just plotting the capacitance function. It seems like a membrane, but it's not. It's just a mathematical function that's simulating the volume variation of the chamber. So you can see it's like you are admitting blood, so you are increasing the volume, and then you start the compression and you start the ejection through the aortic valve. So you see, I thought this idea was so simple, and it worked pretty well, at least for the simplification we wanted. And this is probably is the right one. This is the solution for the 3D. So you see the turbulence, everything is the formation of vortices is nothing related to the 2D simulation. But we have lots of interesting features happening here. So this is what I wanted to show you, Pochi and Hugo. If you think about the modeling, you remeshing, the digital twin of a heart or the chamber, it's really, really expensive and complicated. But sometimes these simplified model can be useful. I don't know, maybe. So this is really interesting. And to finish here, I want to share with you some observations about the pandemic, the 2020s. There, we were locked, and there were two contributions, collaborations that for me, they were not only important, but they were vital. One of them is with a group there in Unicamp that we call CRIAB, that was idealized and today is mentored by Professor José Martinez. Here we have Thiago. Thiago is part of the group, where after that disaster in Brumadinho, Minas Gerais, because of a failure of a dam break, this group organized and until today study mathematical aspects involving the building and the safety of dams. So this is an important group for me. We have some contribution. Here is one paper, totally different. It involves some Venn equations, hyperbolic problems, pretty nice. Also trying to find out how to use discontinuous Galerkin in these problems. Not easy. It's much better to use finite volumes, at least so far in our experience. But we didn't give up. We are also trying. And these are all the possible simulations involving dam break, but here is difficult because you have an initial state where we have zero water. It's a dry bed. So it's much more complicated because one of the unknowns is the water height, but some parts we have no water. So to track this front where you have no water is really challenging. I have also a movie for this interesting simulation here. Let me try to find it. So this is the simulation is pretty simple. So you see, part of the domain is dry, and after the dam broke, and you have again the drying of the surface. So it's not easy to track this changing where now we don't have water anymore, it's drying. And this is actually, at least it was new for me, it's pretty nice, we keep studying that. But this was one important collaboration. And the second one was an invitation by Poti. He was at that time writing, right before the pandemic, collaboration project with Michael Finnick, he's here. And Poti called me and asked, Michael, we want to participate in this. And I said, okay, I want. And we wrote a sprint project to FAPESP, submitted to FAPESP, but then the pandemic came. And the project was put on hold by FAPESP, and after some time it was canceled. The call was canceled. So Poti asked me, okay, so you are interested in that. And the title was Industrial Mathematics for Additive Manufacturing. So we have another group from Sweden, and probably we can create a group and start studying, but they work with optimization, topology optimization. And I also accept this invitation. Was really a good decision for my part. And this group was composed by Poti, Giovanni Javeró is here, Roberto Alzas was here, Stefan Cole Anders, and myself. And we had weekly meetings. We met every single week for almost 4 years. And we have some amazing, brilliant ideas there. It was a really good part of my day because we could try things, new things, without the pressure of having results. And the results of this collaboration are still ongoing, but the good part for me were the discussion of the ideas and realizing that I don't know, is this dedication in creating the connection with applied mathematics, the academic part, and also the collaboration with the industry. But I think the most unique ability you have is to bring people together and creating these connections. We were part of the CEPID, and we can see that. The number of the collaborations that were started there are amazing. The numbers of the CEPID are incredible. So your ability to bring people together, to connect people, is, for me at least, is unique. So, Poti, thank you very much. We wish you many long, joyful, and prosperous years ahead, and we are truly lucky to have you with us.
Thank you, Michael. Questions? Alberto?
So you employ that function that looks like a membrane to mimic the variation of the volume of the heart. But I think that you can even use a simpler one, just a constant, how do you call it, that phi function doesn't need to go zero on the walls.
Sure, you can. Okay, in this case, we don't want to mess up with the boundaries because there in the boundaries we have the valves. So we select a phi function that's constant on the boundary. So it's not varying on the boundary. So we didn't want to include this variation of volume there in the modeling of the valves. It was really simplified, and it was pretty hard. The modeling the valves throughout bounded conditions is not the ideal. So the idea is to have all the problem connect to this one, and we can communicate both and have some real profile of the flow entering the chamber. When you just prescribe the profile, you say, I want a parabolic profile, I want a constant profile, and it's not quite physical there. It's a simplification. So we had this, it's really hard to model the bounded conditions there, and we didn't want the phi to vary there. But you are right. You can use a simplified version of the phi function.
Okay, thank you.
Other questions? Actually, I have one. In the black oil simulation that you presented, that strategy it's much similar to that sequential full implicit method of Jenny. Are you aware of this sequential? It's similar thing, or is
in the end, depends on how you code everything. It's hard to say what's more like efficient or simple. Depend on what you have in hands. For example, if you have a good Newton method, then you can solve for the whole coupled system. I think this one is the best strategy. If you can afford for that, it's the best one, because everything is solved coupled. When you decouple the systems, you have this problem. The conservation is not guaranteed anymore. In our algorithm here, we cannot guarantee that the sum of the saturations is 1, but you saw it's pretty close to 1. So I don't know how to, I need to check and compare, but really depends on what you have in hands. You understand?
Yeah, you have a Newton loop that is inside.
The only Newton loop that we have here is for the flow.
For the flow. Right.
It's just like Javier Tomás for Newton, because you have velocity, fluxes, and pressure. The Newton is there. So it's really, really simple for us, because actually the way we are proposing the coding of that, if you have mixed problem for the linear Darcy flow, you can plug and use it inside this Newton. In each Newton iteration, you solve a linear problem for flow. That's just the code that at least some of the groups I know that work with that have mixed formulation, mixed method coded. So can use this code. You don't need to create a new one. So it's pretty nice.
All right. Thank you. Thank you for your presentation, from oils that are black to square hearts. Thank you. Thank you. Our next speaker is Giovanni Haveroth. Giovanni is the last addition to our group here in São Carlos. the latest one. All right. All set? Ah, okay. So it's so it worked. All right, all right. So thank you, Giovanni, for accepting the invitation. And Giovanni is going to talk about the topology optimization as work that he's been doing in the last years. All right, so Giovanni, thank you. Floor is yours.
Okay, test. Hi, everyone. So I would like to start saying that I'm very happy to be here at this workshop in celebration of Professor Poti's birthday. So thank you very much for the invitation. Well, you see, some of you may think that I generated this figure by AI, but you see, yesterday we had a lot of section of photos and so on. Sorry. Okay, so my talk is advances in topology optimization for metal additive manufacturing components. So sorry, I first met Professor Putin in 2021 when I started to work in a postdoc project on, of course, topology optimization for AM. Along, I don't know, 4 or 5 years. So the presentation is follow this structure. So first I will describe the additive manufacturing problems that may arise, that we may face when we try to print something, right? Some complex structure, for instance, and how topology optimization can be used to improve this manufacturability, right? So in the following, I try to present some of the current strategies that try to solve this kind of problems, this kind of issues, and then I would describe some contributions of our group to solve these issues, right? So to help me to show our works, to point to our works, I will need the help of someone. So Professor Puti will help me to point the works that we did together. And then I will give some potential future extensions, or at least directions. Okay, the first ingredient here is topology optimization. Topology optimization is a method that is used to find the best distribution of material in a given design domain in order to improve some efficiency, some performance for a chosen criterion. So here you see some examples of applications of topology optimization. And I would like to say that topology optimization, or TO, is closely related to sustainability principles, such as research efficiency, waste reduction, and energy performance. Okay. So the second ingredient is the metal additive manufacturing, AM process. So the AM, it's a fabrication process that allows to build very complex structures by depositing successive layers of material. This is in a systematic way. So here you can see very complex structures that are built using additive manufacturing, especially metals, and that are maybe impossible to build using subtractive classical methodologies. Well, we have several kinds of additive manufacturing process. I can see here the powder bed diffusion, or PBF, that probably is the most relevant today in the industry, with the laser and electron beam based systems that change, of course, the heat source, but also the manufacturing conditions, LPBF or EBPBF, DID, and many others. It's important to say that all these processes have advantages and difficulties and limitations, constraints that must be considered along our manufacturing. Okay, so AM is also related to sustainability principle as the waste reduction, since almost all material used in the process become part of the final structure. So you may notice that there is a great synergy between topology optimization and additive manufacturing. So the the TO, topology optimization, is here. So until the 90s, the topology optimization was almost purely conceptual, because you could create very complex structures, but were not possible to build. So it generated complex geometry, but additive manufacturing changed that, because now additive manufacturing can allow to build very complex structures. But all manufacturing, additive manufacturing process have some kind of constraints. And these constraints now can be incorporated into the topology optimization. So closing this circle here. So you use a TO to generate complex geometries, but you can use additive manufacturing to build it. But additive manufacturing have some constraints, and you can include these constraints into TO. This step here is optional, actually. This gives origin to two different fields. All right, so let me describe briefly how AM works. I will describe the technology EBPBF. So the idea is the powder particles that are here are deposited on the over build plate by gravity and then leveled by a rake system. Then some heat source, in this case, the electron beam, selectively sinter or melt the cross sections of our structure in order to create or design in a layer by layer fashion. This movement is done by this set of legs. It's a little different with concern the laser powder bed diffusion that uses mirrors. Okay, so once one layer is finished, the build plate moves down, and a new layer of powder material is deposited in this process follows. So, okay, so once this build process is finished, the build plate moves up, and then this partial sinter material or the powder material are removed to be reused later. And in this case, we have the design already ready to use or undergo to rework. Okay, so here is just an illustration how some design is built in a layer by layer fashion. The thickness of the layer is about 20 to 50 micrometers. What I can say is that there are several factors that may be considered to don't have defects into the fabrication. We have a lot of possible sources of defects, such as the beam speed, the beam power, the hatching spacing, let me see, many others. In particular, overhang, the overhang surface. The overhang is an effect caused when we have a small angle between the surface that we want to build and the build plate. So when we have a small angle, we may have some kind of defects. In most of the literature, they assume this a critical angle, where below this angle we have defects and above you don't have defects. But in fact, they depend from point to point. It depends on the underlying physics involved in the AM. So just to give you more details about the overhang, right? So to this, I will take a look at this zoomed region here, and we want to build it from bottom to top. So the idea is to include successive layers of materials, and here we don't see any defects because we have the called internal support. The previous supports give an appropriate thermal dissipation for the top layer, so we don't see any defect here. But at some point when the angle is small, we may face some problem. Here we see an warping caused because we don't have sufficient thermal dissipation. The solution in the industry today is to include some kind of external supports like this one. So they create external support that are printed together. And okay, this is a kind of solution. All right, so here, Apati is helping me here. We have two works just to illustrate the problems that we may face. Here we see an increase of draws effect, a kind of defect in the surface when we decrease the surface angle. We see this problem, as well as warping, right? Because we don't have supports here. And the Eiffel Tower, in the red region, we have the Eiffel Tower arc with no visible defects because it was included in a kind of support here that now must be removed, right? And in the blue region, we have two defects, the draws here, draws effect, and a warping, because we didn't consider supports here. So it's very important to study how we include the supports, or some other kind of solutions. So there are a few approaches in the literature today in order to reduce this kind of defects. The first approach is the inclusion of external support as a post-processing step for a given design. So you have a design, and we include external support in some way. In the first case, you include external support, and like this one is a very representative work. You see a lot of external supports, but this approach has several drawbacks. For instance, first, the use of expensive material to build this external support. So it's very expensive. You don't need to use this amount of supports, in fact. And you need to make a rework, because once you have printed, you need to remove these structures. And it's not easy because, for instance, here is titanium. How you can have a hand access, for instance, or tool access to this hole here to remove this external support. So this is a strong drawback. Still in this approach, we developed this work here, where we use topology optimization to use a correct amount of material to find the best place and in the correct amount of material of external supports. So here, for instance, we try to print this cantilever beam, and we look to optimize the amount of supports. All right, so another approach is to make this external support part of the new structure. Now you don't need to remove them. So for instance, if you have some optimize a structure like this one and you try to print, you see that you can't because there are a lot of overhang surface. And then you include a lot of external supports and they now make part of the structures. But the drawback here is that the structure was optimized here. So when you include more material, you are making worse. It's not optimal anymore. And so you have more material here and the rise of sharp corners that may induce stress concentrations. That's not okay for mechanical purpose. Okay, so the next approach is to make overhang constraints as part of the constraints of our optimization process. So there are two ways to do that. The first is using the geometry of the material. You see, we look only for the material of this structure that you want to build. And another one is based on the physics, the underlying physics of the AM. So I will back to these two works and later in this talk to give more details, right? A new approach is to look for the scanning strategy. And the scanning strategy, it's a set of AM parameters, like, as I told you, hatching spacing, beam velocity, and so on. Or heating path, they actually, they must be improved. They must be chosen in order to reduce the amount of the need of external supports. As a new and future work that I'm working with, it's the use of pins as a tool to accelerate approaches to B and 3. All right, so to show the previous approaches, I would like to consider this classical simple TO problem that consists in minimize complies subject to a balance equation and a volume constraint. To illustrate, I will consider this rectangular domain where the structure that we want to find is fixed on the left boundary and subject to some load here in the right boundary. In all simulations, I will use 50% of material, right? So this means that half of this domain is composed by material. So make use of this simple formulation. I have this cantilever beam here. And now I want to build it. For this, I need to define a build plate. That's where our structure is initially supported. And a build direction that follows the layer by layer, the position of material. So we want to build this structure from bottom to top in several layers. All right, so the first approach that I want to talk is about the one that don't use external support. So here we want to modify the structure to make it self-buildable. We'll have self-supporting structures. This work developed by Kian, this author proposed the use of this measure, the project undercut perimeter, as a measure of the amount of overhang in our structure. So the idea is put this measure as an additional constraint into the previous TO problem. So we include here, and making use of this new formulation, we may have a structure like this one. If you compare with the previous, now we don't have overhangs, and okay, we can build it, right? We can build it with no problem, but at a cost to modify the structure, and it's now not optimal in some sense, right? Okay, but the problem occurs when we try to reduce this filter size in order to allow more voids in our structure, make the structures more thin. And we may have the formation of drippings. And these drippings appears and, okay, this structure now satisfy, at least mathematically, they satisfy all the constraints, right? But not physically, because we can't build these drippings without the inclusion of external supports. So, okay, this formulation is not perfect. Still in the strategy without supports, external supports, we go now to our work that is based on the physics of the process. In our work, we propose the use of an objective function composed by two terms. The first one is the same complies used in previous formulations, plus an additional cost of partially built structures. So this term here accounts for each partial build structure cost in some way. So in this work, we propose the use of two formulations, two ways to build this second term. The first one is the self-weight based formulation. The idea is quite simple. The idea is when you include a new layer of material, you consider self-weight. So this new layer will bend over the previous one, and you have displacements. The idea is to reduce these displacements. Quite simple. The thermoconductivity-based formulation, here we create a kind of gradient of temperature between the top part and bottom part. And the idea is that gradients of temperature are larger in regions where you have overhang regions, And the idea is to reduce the amount of these gradients, reduce this compliance. Just to illustrate, okay, so for numerical purposes, we discretize this zero t, that is the time for the AM in L layers. And to illustrate, here is the formulation for the thermoconductivity base of formulation. We have the compliance plus L additional compliance, thermocompliance, where the theta I is the solution of steady state heat equation in each partial build structure. Right? So here is the same 2D cantilever, but in a 3D setting, right? It's better to show the details. So this is the solution using the classical formulation, that is the reference one. Here, using the Kian's strategy, the geometric-based approach, you can see the rise of drippings here. And the bottom results are the physics-based approach using self-weight. I have something like that. You can see that a kind of a column emerges naturally using this formulation. That's similar to inclusion of an external support. And using the thermoconductivity strategy, you can see when we compare with the reference one, you see the reduction of overhang surface like this one. Here, it's closed. So you reduce the amount of overhangs, but it's not eliminated yet. Just to illustrate another case, a jump. Now we go to the approach based on the inclusion of external supports. So we don't modify the structure itself, but include in a smart way the external supports. For this strategy, we use the same layer by layer procedure used in previous work. The idea here is to find the best external support as well as the best orientation of our geometry. See, you can rotate our geometry inside the build chamber to find the best position where we can print with less overhang surface. So this is min-max problem here, where the max here is the maximum temperature using now a transient heat problem. At the right side, I try to mimic, just to illustrate, because you see, the layer is very thin. Here is just to illustrate how we consider the initial temperature. We consider the initial temperature as the melting temperature in the top layer composed by by design and by support. And then after some time, you have some temperature field like this one, and this temperature is used to compute our objective function. And this temperature will be used as the initial temperature, part of the initial temperature in the next layer. So we are trying to mimic, in fact, the AM process. All right, so here just to illustrate application of this formulation. In this graph, we show the cost function over the iterations for the support with, for the design with support, external support. Here, the design without external support, and here, the orientation of our design. So it's more or less like this one. So the black is given. It's what we want to build, and the green is the best support structure. In fact, these supports in green are not solid. They are lattice support. So to make it, to use less material and make the remover easier. Here, just to illustrate two more applications for a 2D cantilever beam and the same 3D MBB beam case with 50 and 100 layers used in your simulation. All right, so until now, we have two approaches. The first one is to modify the structure to make it self-buildable, or at least to make it, well, better to build. And the second one is the structure is given and we try to improve the external support. So now the new idea is to take a look at this small region of our design, and you try to minimize some cost based on the scanning strategy. We look to the scanning strategy. What scanning strategy? It consists of the path of the heat source, power, velocity, spot time, hatching space, that as I told you, that are crucial for the efficiency and quality of the process. So all these parameters are fixed in our work. They are realistic values, operational values, except for the path of the heat source. So we look only for the path of the heat source. For this analysis, we consider thermomechanical problem formulation. Well, we have all the parameters temperature dependent. The motion, well, here the mechanical problem, the loading is given by thermal expansion. And you go to the optimization problem. So the optimization problem is formulated in this way. So we try to minimize this function, looking to find a best path through the beam spot. So we try to find the best sequence of beam spots in order to minimize this functional. And this functional is shows to be this one, that it is the history of the temperature of whole problem. So we compute this objective function along the time and along all domain over time, right? So the idea here is, it's very nice, this function, because it is reading only in terms of the temperature, but is indirectly related to the mechanical displacements, the displacements, because if you reduce this functional here, indirectly we are reducing the loading that we are given our mechanical problem. So yeah, minimize it, we are also indirectly minimizing the displacement. And here, just to illustrate the first two columns, we have the out of plane Z displacement and the residual von Mises stresses for two classical paths, the sequential and the in-out. These two are very common in the industry. And this one was optimized. It's a combinatorial optimization. We used a genetic algorithm, more than 15 days of simulation with more than 30,000 function evaluations using parallel computing, so it's very costly. And we find this path here. It's very nice because you see, we jump from one position to another. 1, 2, 3, 4, 5, 6. So we jump. And this small change in the path was able to reduce in 7% of our residual displacements. So imagine you build a structure, 7% of reduction, we have less warping in our problem. Just change a little bit the path. Okay, we have several limitations here because we are simulating just 1 millimeter square here. So, all right. So that's the reason why we are trying new tools to improve this. Okay. So to conclude, along this collaboration with Professor Putti, we developed a set of procedures to reduce the issues related to additive manufacturing problems. So next steps, we start new collaborations and use of new tools to do that. So that's it. Thank you very much.
Thank you, Giovanni. Very good. Questions? Please help me out. No questions? Oh. Who want to start? Michael. Oh, young. Milton.
Hi, thank you for your talk. So I'm aware this is a weird question, but I had to ask, you have that building direction, the vector B, and you mentioned that you could rotate the structure to find the easiest way to build it without many support structures. But in that scenario, for that thing that you were building, could you also change the plane? Like you were building from bottom up, could you shift it and build it from the other side? Because when I look at it, it looks like you wouldn't need support. Can you do that? Is that too?
In PBF, no. In PBF is one direction. But there are other kind of machines like the DAD that I mentioned here. This DID, it's how I can I translate to English, solder. It's like so you deposit layers in a layer. You are including material, solid material, but at the same time you can rotate. So you can build in different directions for this machine, for example. But the PBF, no. The PBF is the most employed in the industry today. And no, it's one direction, and you can't actually finish. And okay, now I will rotate and continue. You can do that.
Thank you.
Okay. Oh, thank you very much. So was this mainly about additive manufacturing of pure materials or alloys? Because I think with alloys, an important issue is then the microstructure and what has been the cooling rate at each individual point, which may then introduce more constraints into how one would want to produce.
Yeah. We work only with titanium, but of course, for instance, this point melt strategy, it changes the microstructure as well, and it was not studied. But yes, we have a lot of constraints because it changed, for instance, the internal stresses in each melt pool, and it changed everything. So in fact, it's very hard work actually. The physics is very complex, and here is just a simplified one.
More questions? No? So let's thank Giovanni again. Thank you, Giovanni. So now we go for coffee again and poster sessions. Please take your time to visit the posters and talk with the people presenting there. And don't forget to vote. You don't need to vote today, but it's would be wonderful if you could vote by tomorrow lunchtime, all right? So we can account for the best poster. Let's go.
Será que foi?
Não tá. Agora parece que vai. Foi. Hugo, você quer usar esse aqui, ó? Paulinho, sinal verde, até 2. Hello, good afternoon, welcome everybody. Let's continue with our session. Is the last one in the afternoon. It's a pleasure to introduce here Hugo Luiz Oliveira. Hugo is also a good friend. He is collaborated with us for some time. He did his PhD here in the structural engineering and was a postdoc of Professor Cuminato. And now he's working on structural engineering department of University of Campinas, right? So Hugo is gonna to talk about computational mathematics applied to Whitley valve and hard valve mechanics. So it's a very, very interesting work. Okay, Hugo, thank you for coming. Thank you for accepting the invitation, and the floor is yours. Thank you.
Hello, hello. Can you hear me? Yes. So, so for me, it's a great pleasure to be here. It's a great day for Poti and for all of us. So I'd like to thank the organizers for inviting me to be here for this birthday to Poti, for this celebration. It's a very special moment. And for me, the history with Poti starts in 2021, just after the pandemic, in which he, as I think it's clear for everyone here in this audience, Poti has a very broad, let me say, set of interests, and one of these interests that was at that time was exactly this this heart valve, which is called Whitley valve. So at that time, Professor Poti told me about this problem, and we started to collaborate on this, and we discovered things so interesting that actually it was a change in terms of career for me. And these days, I still continue working in this kind of problems and trying to target to this area of studies. So all of that thanks to him. So let's talk a little bit about it. Not forgot to mention, this is also a collaboration with other colleagues, very good friends nowadays. For example, Professor Sean McKee, that also in the audience, and other colleagues like Professor Ian Stewart in Glasgow, David Whitley, and many others. So it's a very interesting group. Well, what's the motivation? So the motivation for this, in order to explain, I would like to say that, you know, this is the human heart. And in the human heart, we need to respect a very specific direction for the blood flow. Okay, if this blood flow is not flowing in the right direction, in fact, we have some problems. Okay, and what governs this flow is the functioning of in the very specific synchronized way of these four valves. Okay, in the pictorial manner, here we can see these four valves, and our focus today is exactly this valve here, which is in the base of the aorta, and which sends blood to the rest of the body. Okay, the other two are the mitral valve, and also this other valve here, which is the tricuspid valve, and we also have the pulmonary valve. So what happens? What happens is that when we have, for example, for certain reasons, including aging, including fever, rheumatic fever, for example, okay, sort of pathogenic conditions, people can develop very serious problems in these valves, okay, when they starts not to closing so well or not to open so well. In either case, we need to do something about it, because it's a condition that needs to be treated. And what the technology today, what's the best practices today, what doctors do is illustrated in this video. For example, here we see a healthy heart, okay, working. And here we see the aortic valve, which is one of the objects of these studies. So once this aortic valve is not working so well, in this case here, we are seeing one of these pathology, which is called stiffening. What we do actually, the doctors does, they take this valve out. So it's a surgery, it's an open heart surgery normally, in some case. But here in this video, it's a way in which you do not need to open the chest of the patient, but actually you use a catheter in order to access the interior of the heart. So you access that, and then using these catheters, you can place a prosthetic valve or a prosthesis, actually. It's an artificial valve. And this process that you are seeing here is what we call the crimping, in which you fold the valve, and then you put that inside a catheter, and then you deliver it right in place where it needs to be. You need to take some cares, because actually you cannot block this small hole that you see here, because here is the coronary arteries. You cannot block that, because otherwise you can have some heart attacks. So it's a very complex problem. It's a very challenging also from the engineering point of view, because you need to design this valve in order to stay in place, to be delivered, and after that to start functioning again. Okay, so these days you can do that in some minutes. After that you can come back to home and have your normal life. So, okay, if you go to the literature or in the market, depending on your condition, you have plenty or a sort of a big set of options available for you. So the last time I counted that, it was available more or less about 60 types, different types of valves. And this is just to mention that there is not only one valve that works for everybody in every situation. Actually, it depends on each person. So even if you choose the best, that's what's considered the best valve today in the market or in the literature, you're still not, let's say, free of problems. So in some cases, you need to take care about, for example, the thrombosis. Okay, so thrombosis is something that happens when you have one of those valves, and if these valves are synthetic, I mean mechanics, since this material is not compatible with the biological tissues, normally your body will try to fight it and producing thrombus. So we don't want that. So that's why we need to take anticoagulant medicine to prevent that. Also, in these valves, since it's a prosthesis, we can have tissue overgrowth. We can have also infections, leakage. So it may happen, and also failure by fatigue. Of course, technology is being improved. We have so far about 60 years this technology is being applied and developed, but we still have these inconveniences. So thinking about this problem, Professor David Whitley, which is one of the colleagues that is developing this work with us, actually he's a doctor, he's a surgeon, and in his practice he saw in his mind one particular design, which is this one, which is, you don't find this design as, actually, if you compare to the available designs here, which we always try to mimic what is already inside the body, okay? But Professor Whitley advocates that if you change the design and use this S-shape geometry, actually we can avoid many of these problems here. And the main problem here would be the thrombosis or thromboembolism's effects. And why of this? For some reason, when the blood passes through these valves, okay, these synthetic valves, let's say, the blood loses its capacity to wash itself. And this is a natural phenomenon that happens. But for some reason, it's still not fully explained today. Still open in the literature. We don't know why, but we don't know. What we know, actually, is that once the blood passes through a synthetic valve, it loses its through motion. So Professor David thought about this design because in theory, okay, when it closes, since you have these leaflets, okay, that is curved, so it helps the blood to recover its motion and starts to swirl again. And this swirling motion is exactly the one that prevents the blood to form the thrombus. So I don't know if this will actually we are trying to demonstrate that, at least from the computational point of view, we have some evidences, but still remain to be demonstrated in experiments. But for sure, if that is demonstrated, I'm sure that Professor David would be one of the main let's say minds that would revolutionize this field. Sure, okay. So, Professor, this is one of the sketches that Professor Whitley started thinking about this problem. This is one of the prototypes that he developed in the previous versions of this valve. And Professor Sean, which is here in this audience, inspired by this schematic representation here, developed a mathematical representation of this, because then, up to this point, we didn't have actually equations to describe these leaflets, okay? At least in the parametric way. So thinking about this, Professor Schoen developed these equations based on level curves. Actually, you can use circles, okay, in different radius. And as you know now, Professor Schoen is a great fan of geometry, yes, Euclidean geometry. So he has his ability to find, yes, very practical explanation for the shapes. And based on that, we can parameterize these curves and produce these shapes. What is nice about it is because from the design point of view, it's very interesting if you have this equation, because now you can say, okay, for a certain set of parameters, height, diameter, or the curvature, you can try to find the best way or the best shape for this problem, okay? And this work was actually shared to the community, with the community in 2021. That was before my arriving in the group. But they had already this notion very clear that, okay, it's possible to do that. And also it's possible to mimic the positions of the valve opened and also closed, as you can see here. Yes, and it's very close to the prototype we saw in the other figure. So the thing is, here we can see other geometries which is also possible to build using those equations. And here, sort of exploring one or another feature, because here, as you can see, probably we see here a sort of a loss of continuity of the normal vectors of these shapes. So here we have a discontinuity. But if you include the continuity, if you enforce the continuity, you can have a smooth space here, and we have some interpenetration here. This is not physical, it's not possible, but at least you have a smooth description of the geometry itself. And what is very nice about this geometry is because actually you can build this geometry from a flat sheet. So from a manufacturing point of view, it's very interesting, okay, because you simplify the manufacturing process. So all of that was developed, and then if actually Professor Sean, yes, started to generalizing these ideas, and nowadays we have equations to describe not only two leaflet geometries, but 3, 4, 5, and so on, which is very nice, not only from the heart valve applications, but also from architectural point of view, because this can be used to build thin structures, and where you need to deal with this kind of curvatures, okay? So, well, but what was the problem here? The problem here is that these shapes, as you can see, is a parametric design of the leaflet itself, but it cannot predict the actual movement of those leaflets because it does not respect the first principles of mechanics. So then we started thinking more about this problem, and we tried to bring mechanics, or the classical mechanics, to this problem. So very briefly, what we did actually was using the compatibility equations. Where is Bruno here? Yeah, Bruno. So nonlinear compatibility equations here, in which we take in consideration also even the large displacements, but also the large strains that we can have in these problems. I'm not going to detail on that, but that's just to mention that here we use the nonlinear relation between the displacements and the strains here. So the greens, actually this is the green tensor, the green Lagrange strain tensor. The problem is, if you try to describe the kinematics using this tensor, you cannot use anymore a direct relation between this stress and the Cauchy stress, or the true stresses that we usually find in solid mechanics. But as you can see here, here we have the strong version of the equilibrium equations. But I do not use the strong version in this problem. We use actually a weak version of it, using the finite element method in order to do all the calculations. And we, instead of solving this equation, actually we have two options. We need to build a strategy to compute the actual configuration of the valve, because now we have large displacements, and we have these two options. Either you use the updated Lagrangian formulation, which can be problematic in some problems, because since you don't know where exactly the configuration is, you need to predict, or you guess one, and then you advance the problem and try to converge. Can be, but it can be problematic in some cases. And in our case, we use we decided to use the total Lagrangian formulation, because here we have actually a clear relation between the second Piola-Kirchhoff stresses tensor and the green strain tensor that I mentioned before. So it's very convenient for us. But this is from the solid mechanics point of view. But as you can imagine, based on the problem that I showed in the beginning, we need to simulate also the blood. But before that, let me just to call your attention for the fact that, as Bruno really well said in the previous talk, you have many alternatives, or many ways to establish a constitutive relation between these two tensors. In our case, we decided to start with the simplest case, which is this one, the Saint-Venant-Kirchhoff model. And in our first results, it didn't work so well, because you overestimate the stresses, so it's not realistic. After that, we started to use the Neo-Hookean material, or material model, because it's in the bioengineering field, people like very much this model. But in our simulation, it didn't perform so well. So we decided to move to Mooning Riley, and then this one started to work better for us. But what really was good enough was this Ogden material. So the organic material was the formulation that we kept for the next stages. Now, for the blood itself, actually, not yet, but just to mention that, once again, this is many choices that you need to do. But in our case, since you have, for the leaflets, it's a very thin, let's say, flat faces, surfaces. In our case, we decided to use shell elements. The problem with shell elements, you have many formulations. Some of them are more stable than others. We tested many of them, but the one that I would say that I would start today, okay, and that that's my advice for today for anyone that wants to start in this field, is using this element, which is called the Bellic-Colin side shell formulation. It's a very interesting formulation and has these degrees of freedom. So we have not only displacements and rotation, but we can also describe what's happening along the thickness of the shell. So it's very stable, it works very well, and you can do nonlinear analysis with it. For the fluid, it's Navier-Stokes, the classical Navier-Stokes. In our case, we decided to use, actually we used the finite element for that. Could use finite volume, but in this case, we stayed with finite elements. So this is the weak form for the fluid. And in our case, it worked very, very well. The fluid is incompressible in this moment, could be compressible, but for these simulations that I will show you in a minute, it was incompressible. What also is one of the particularities for this problem that makes it very hard. Actually, when you try to model this problem, because we wanted to simulate the valve inside the fluid in real conditions, the problem is that once the fluid passes through the valve, it's the fluid itself that opens the valve and also it closes the valve. And for those of you that try to do that, actually that try to work with fluid simulations, you know that one of the problems that actually Michael told us today is that your domain remain fixed, okay, for that particular time step, but you have something that needs to move. But if the solid is moving, so the fluid needs to move with the solid in order to not have the gaps. So how do you do with it? In our case, we use this Além description, which is an arbitrary formulation in which we actually deform the mesh up to the point that the mesh is too deformed. Once it's too deformed, you stop the simulation, remesh again, and then you project the results in this new mesh, and then continue the simulation. Okay, so this was the strategy. The problem with it is that you need to reformulate all your problem because now you have the velocity of the mesh itself that needs to be taken into account. And then you need to rewrite all the equations. It's doable, okay? It's something that it's available today. It's not a problem. But just to mention that we need that in order to simulate our problem, because otherwise we would need some kind of, that's why Michael, for example, he showed a way to do that without doing this formulation, okay? Now, we started simulating. So here is the dry test that we call. We tried only test in order to check if the valve was opening well. So this is much more reasonable from the physical point of view. Here is a picture from above. What we can see is that when the valve opens, we see the leaflets trying to fold over itself. And then you have these stress concentration zones that start to appear here and also here in the base of the valve, which is natural and expected. But also, to do that, you cannot do that actually if you don't have a very good contact model. And for those that are familiar with contact mechanics, know that it's very hard to have contact stabilization between very thin surfaces. And also if this first, particularly if this surface is flexible. In this case, very flexible because it's nonlinear. So everything here is nonlinear. The contact is nonlinear. The formulation, you have big displacements, large displacements, large strains, contact, and also the boundary conditions also is nonlinear. In terms of closing, when you try to close the valve, you see this pattern, okay? The valve, it really, when it closes, you have a twist in the center of the valve, which could actually help to demonstrate the idea that the intuition that Professor David had in the beginning of this design. So at least from the mechanical point of view, it makes sense, okay? Well, after that, we decided to include everything in the same model, so using the full fluid structure interaction model. So in order to do that, we separated the leaflets in 3 sheets, and these 3 sheets were actually placed in a rigid ring or a stent. We call that a stent, and that was placed using these material parameters that I'm seeing here, using the Ogden model. This was placed inside this domain. So this domain is a 3D domain which simulates actually the blood region. Okay. And this geometry is done like that because these parts here is called the sinuses, and these sinuses are actually the aortic root. So the heart is on this side, and the aorta is here, more or less. And those 2 pipes that you see here, small pipes, actually are the coronary arteries. So we tried to simulate that. That was our first try in our group, and actually we could demonstrate that. And the simulation was working, and everything was as expected. The contact was working, the fluid was actually working as expected. And then we decided to progress and invest more in this direction, because as you can see, the boundary conditions here are too close to the valve, so we tried to expand the domains. Here is actually the same simulation, and this is the mass flow. Just to mention that if you see this behavior a long time, you can see that it's a very nonlinear problem. So if you try to simplify this problem, it will be, you cannot have a very good result because of that, because everything is nonlinear here. In terms of blood flow, what we see is that here is we see as isosurface of the blood, and you see this star shape, which is produced by the valve itself. That's not common because this is a particular design, and can be used in very good manner. We can try to explore that, but what we observed that this is a very particular behavior for this valve. Okay, that doesn't happen to the others. Here is the idea that I told. So we expanded the domain just to see if there was no interference or of the boundary conditions into the behavior that we were measuring here. And with those simulations, we were convinced that okay, that the choices that we took here in this project was good enough for our purposes. Then we tried to validate that. So we took actually Professor David had one of those prototypes that were tested in laboratory, and we took the geometries here. This is just the details. We can find it in this work here. So we draw the geometry as best as we could, and we actually just to explain a little bit the experiment. Here what we see is the pulse duplicator, and this pulse duplicator is a machine that actually mimics the heart. So it produces heart cycles artificially, so you can test the valve that you have in mind. So you take your valve and then you place here in this point, okay? And then you measure the flow pressure and things like that. So we had that. And here is our model for this particular experiment. So we don't simulate the whole post-applicator, so it's not a closed circuit, okay? And here is the experimental pressure drop that was measured for this valve. So we apply this pressure drop, and then we measure the flow rate. And here you can see the comparison of the experimental one, which is the green one, the green curve here, and the blue one is the model one. And as you can see here, for opening and closing is a very good match for them. For engineering purposes, you are very happy with these results. The only thing that is not really well explained for our model actually is this part, because in terms of modeling, you still have these oscillations, which is actually, if you compare to the experiments here, you also have oscillation, but it damps out much faster. The explanation for that is because the experiment, you have the post-duplicator, the whole post-duplicator. In our case, we don't have it. So in order to fade this out, you could actually either add damping or simulate the whole circuit, which was not the case here. So here is a comparison of experiment and simulation time to time. And many times here, we have a very good match between it. And here is a small video in which we can see in the center the experiment itself. And here we have the velocity profile, and here the residence time for this valve. With that, we were happy about our model, because now we could have a computational model that could capture the actual behavior of this valve, which is very complex. And then, particular Professor David was not so happy about this phenomena here. Okay, if you can see here, when the valve closes, it not only closes and stays as it was in the beginning, but it bends a little bit in the center. So you have a bending in the central part. We call that central bending. Professor David, from his point of view, he would like to keep that shape actually in the right position. So we started to think about this problem, and we did many parametric studies, and we could not improve this phenomena. Here you can see that if you decrease for example, the height of the valve, this phenomenon is still worse. So, okay, there is a relation between the height and the other parameters, but it's not the right answer. Here another picture just to show what happens to the stresses when you try to vary the heights. But actually, you always see, in some degree, this bending in the center of the valve. So he didn't like that. So we tried to study this problem, and this is one of our latest results concerning this problem, because Professor Sean, that is here, he discovered that actually we can draw some straight lines in this surface, and they meet at a common point, and we could potentially use these straight lines along this surface as strengthening points. So what we did actually was, okay, let's put some stiffening structures along these lines and see what happens. And we see that, okay, if you don't strengthen anything, you have this central bending. If you start with 3 stiffness here, you have more or less stiffening this region. But if you have 6 stiffeners per leaflet in the right position, you can actually sort of eliminate this central flexure here. Of course, it is not, there is no free lunch. If you stiffen the closed position, you also stiffen the open position. So it becomes harder to open the valve also. So we need to take the balance from the design point of view, okay? But we are still working on this problem. And Another interesting problem for the same model. Actually, as I mentioned before, this is a phenomenon that was actually pointed out by some doctors in the late 80s. They thought that actually the blood does not come out from the left ventricle in the linear form, but also actually it was in a helical flow. These days, so we have a demonstration. You can actually see that using this kind of 3D magnetic resonance. It's possible to do that, and you can demonstrate that actually this is the case. As you can see here, you see this is real motion happening, and we decided also, okay, let's take our valve and let's try to reproduce this. Let's see what happens. So here is the part of the thoracic aorta, so it comes from the heart to more or less half of our back. Paying attention to the coronary arteries and also the superior arteries here. So we plugged the valve here and tried to reproduce the experiment again. So here is the mesh, the finite element mesh. As you can see here, this part is more refined. And for this problem, we're talking about roughly 14 million degrees of freedom. So you cannot run that in this PC anymore. So you need a super PC. And we tried to run that here in Euler, and we could. It takes some days, but after some days, you can simulate. You can have the results. So here we can see some of the fluxes, flux path here, and as you can see. There is this jet here being formed in the center part of the valve, and particularly two challenges in this problem. First of all, is how do you simulate this, because the through motion needs to be before the valve, so you need to impose boundary conditions that is turning the valve, the blood itself. So how do you do that? So we managed this in order to solve this problem. And once the valve closes, you see here, for example, when it will close here, you see certain, the vector shows some activities in this part, especially when it's closed. So you can see here. And at least from the mechanical point of view, that could be an indication that the washout, the so-called washout effect would happen in this domain. So this project was, after that, actually, we started a collaboration with Professor Pablo Blanco, which actually has a full model for the body, so you can plug. The idea was to plug our model inside his model. What's the idea here? Because if you could do that, actually you have a virtual laboratory in order to test new valves. So that's basically the idea. This project is still not finished. But once again, still with Professor Poti, we started to work in this project, which is a full heart model. This is the digital twin of the heart itself. And we started to collaborate it with the guys, some guys of ANSYS, in order to create that. And the idea here was to have the full physics in order to simulate actually a real heart with the blood. Here we see the wave propagations in terms of the electric pulses, also the ions balance. So everything together in order to have a digital platform for testing valves. So this is now free, available in the internet. You can just find this ANSYS Heart library, and you can do these simulations, and all the explanations are there. And just to finish, also with Professor Poti, we have collaborated with INCOR, which is a great center here in Brazil for the heart. And the idea was developing pump hearts for children, okay? And this project is still an ongoing project, and we are still having results for that. And another previewed experiment that we were demand that are coming to our group now is trying to simulate this catheter for people which suffer from diabetes, which needs to take medicines, and the doctors actually say they know that depending on the position that you put this catheter, the medicines work well or not, but they don't know why and they don't know where. So the idea is to simulate it and try to bring an answer to this question. So just to very quick here, the idea, at least from my perspective, all these results, just to show you that all of it started in 2021 when I met Professor Poti. And for me, I'm pretty sure that I would not be in this position here today and working in these projects, wonderful projects, if he or Professor Sean also would not opened the door there. So for me, it's a great pleasure. And this is a quotation from Isaac Newton that say that, okay, if you can do great things, it's not because you itself, but it's because you are on the shoulders of giants. So in my giant gallery, certainly Professor Poti is there. So thank you, Poti. Have a very nice happy birthday. So thank you.
Thank you, Hugo. Questions? No? Roberto?
Thank you, Hugo, for this wonderful presentation. About the material, the material can be considered incompressible to some extent.
The material, yes.
Yeah.
The solid material, yes.
So when you try the Neo-Hookean with penalization, perhaps that's not the best option, and it's better to try to impose incompressibility by pressure, like in the Stokes problem. And did you try anything in that direction?
No. At that time, I didn't try it.
But is that available in the ANSYS models?
Yes, that is. Yes.
Álvaro?
Excellent talk.
Thank you.
I noticed that they're using LS Dyna.
Perfect.
Did you ever try the new isoparametric shell elements available in LS Dyna?
No, for this problem, no.
Try. You know what is isoparametric finite element?
Yes.
Yeah.
Yes.
I mean, further continuity, smoother things. I believe it's. I'm sorry.
Yes.
Yeah. I think so.
Yes.
It's, it will be something that
could be very good. Yeah.
Because it's being. I mean, the industry is coming. Those shell elements are slowly superseding the standard Belichkot size shell elements, which has been the workhorse for large deformation shell analysis for years.
Yeah.
But the isoparametric arena is changing this bit.
Very nice. Yeah.
Okay.
We can test it. Yeah. Thank you.
Thank you. Let's thank Hugo again. Thank you. Just long press to, no, it's off, but long press to. It's my pleasure to introduce you Professor Michael Winicki. Michael is also a long-time collaborator here with Poti, and he's from University of Limerick, and yeah, it's collaborating quite a long time. He has a book co-authored with Professor Cuminato, so they have a history together, right? Might I say? And you saw a picture of us having lunch on Tokyo, so it was very nice. So, Michael, floor is yours. Thank you.
Okay, thank you very much. Thank you for advertising the book. I was too shy to do it myself, but you've done the hard work for me. Okay, thank you very much. So this talk, modeling gas flow in an industrial countercurrent moving bed reactor. This doesn't really have any link with Poti, I'm afraid, unlike all the talks, but certainly some numerical issues which come out of this, which it would be useful with some Brazilian numerical expertise to resolve. So I'm basically at the University of Limerick in Ireland, but still affiliated to KTH Royal Institute of Technology in Sweden, and actually that's where this particular problem came from. So the first thing we'll need to know is something about blast furnace iron making, and then we'll get on to the how to model gas and solid flow, which is what we have in one of the things we have in a blast furnace, then results, and then conclusions. Let's see, I have a lot of buttons here, so I have to make sure I'm okay, so blast furnaces, well, these exist all over the world. I think in Brazil, there's maybe, I couldn't find any current data, but maybe about 20, 25 in all different parts of the country. And so this is an efficient way to produce iron. And the idea here is, I probably need this, is that we dig up iron ore out of the ground, and then we combine it with coke pellets. Oops, sorry, and that gets fed in at the, oh, too far. Nope. See about here, I think. And, I'm just trying to find the. Oh. Oh, well, oh, this one here, isn't it? Oh, on the side. Oh, that one. Oh, yeah. So yeah, so coke and iron, coke. Sorry, yes, yeah, coke and iron ore are fed in at the top here, but hot air is fed in from the bottom, and the idea basically is that the hot air will rise, the coke and iron ore will fall, and then there will be exothermic chemical reactions occurring in the center here. Eventually, the coke and iron ore will get at a high enough temperature that well, not quite melting, but sintering, and then we'll just get droplets of iron coming down here, and then all the iron is collected eventually at the bottom here, the hot metal, and then that's used later on for production. So the people that make or rather design these things, they have quite a sense of humor. There's a region here called the Dead Man, which is just a solid coke deposit which accumulates here with time. This geometry, it's really three-dimensional, and so if we imagine like a torus going around here, then there's this region called the raceway where the hot air is actually blowing around, but there can be particles trapped in there going around with it in the way that you might have on a Formula One racing track. I think we can probably then go to the next one. So what's really happening There, this is just a schematic, but now in terms of the temperatures and the chemical reactions which are occurring. So we're going from then from bottom to top. We're at higher temperature down here. That's where the air is being fed in. Then as we go up, the temperature is lower, but then there are all these various chemical reactions which are believed to occur, in particular as the iron oxide is reduced just to iron. But there are actually two temperature curves here. One is for the temperature of the gas and one for the solid, so we don't really have full thermal equilibrium here either, although that's not what the main part of this talk will be about. The background for why we're doing this project. So there was this EU project with the acronym BLEMAB, so Blast Furnace Stack Density Estimation through Online Muons Absorption Measurements. And this is the idea that muons can come from space, and we in principle can detect how much we have of them. So then if one were to place a muon detector, let's see, I think now we want to be looking at this one. This was a previous project, but now the ideas have moved on. We put a muon detector here, and then we have it detecting, we're trying to detect along a straight line out into space. Then in principle, muons would come down, we would detect, and we would take some readings here, and that could help tell us what is actually going on inside a blast furnace. Because the sketch that's given on this previous slide, well, no one's ever been inside one. And the only idea that people, let's see, yeah, I don't know, maybe don't need it. The only reason people know that the schematic looks like the one I had and why it might look like the one is given here is actually 1960s and 70s blast furnaces in Japan. They were quenched, so the temperature was decreased very quickly, and then just cut open, and then people could see, oh, that's what it looks like. But these things are actually 20 meters high, and the radius is about 7 meters, so one doesn't want to be quenching these too often. So, okay, so now, but of course, people will then try to use mathematical modeling to try to figure out what is going on in there. So the first step, in spite of all this thermal gradients and chemical reactions, is to understand the gas flow. So this would be the simplest schematic we would have for this. We'd have the gas coming down from the top, air coming down from the bottom, and then I've put on the dead man here. Then gas inlets here and there, solid inlet at the top, and then, well, some solid does manage to get through, so then there's some solid outlets down here. Then the figure on the right-hand side, well, that's just the geometry now, and for this talk, we'll just be pretending that the situation is axisymmetric, although it's not quite in reality. So then this is giving the dimensions 20 meters high. Here, well, radius slightly less than I first said, but the right order of magnitude 5.6 meters. This dead man region might be about 3 meters high and about 1.6 meters in a radius. So this is then essentially we're looking at a gas solid flow. This is actually then a counter current moving bed reactor. Solid is trying to come down, but the gas is coming up. The solid, which is actually not just one substance, but it's coke and iron ore, collectively known as the burden, that's fed in fact, layer by layer from the top. So the previous slides I had where we had this stripy configuration, yeah, that was because we're feeding one layer of coke, one of iron ore, and so on. The densities of these things, so coke is about just over 1,000 kilograms per cubic meter. The particles, they have a characteristic of about a diameter of about 5 centimeters. Iron ore, well, slightly heavier, but slightly smaller in size. And then there's the gas getting blasted in through the tuyères, so that's the pipes at the bottom, maybe coming in at 1,500 degrees centigrade, and flow rate of about 120 kilograms per second. So how do we model this kind of flow? Well, so one approach which is gradually getting more and more popular is then to use the discrete element method, and there is even a software, I think it's called EDEM, for trying to do this, but that's still computationally expensive when we think about, well, the geometries of the furnace compared to the sizes of the particles. You would need billions of particles to try to model that, and that's just the gas-solid flow without getting into the heat transfer and the chemical reactions. So then there are also continuous approaches, various different versions of this. One thing called the kinematic model, where one assumes the velocity of a solid particle in the radial direction is proportional to the radial gradient of the particle velocity in the axial direction. Also, one finds what's called a potential flow model. That's saying then that the velocity of the solid phase is assumed to be proportional to the gradient of velocity potential. So then those of us who've done undergraduate fluid mechanics, yeah, that will mean we'll know that as being a characteristic of an irrotational flow. And then there are also what's called viscous flow models, where the solid flow is treated as a continuous flow of viscous fluid. Of course, this all seems rather strange, that this type of flow, irrotational flow, that's what we're familiar with for inviscid flows when we do basic undergraduate. When we do basic undergraduate fluid mechanics, but yet on the other hand, the same process is being modeled by other people with a viscous flow model. So here I'm just going to focus on the an Euler-Euler viscous flow model. So just Euler-Euler because of the two phases, and then we'll actually see how it is possible that we get from that description back to the potential flow in some sense. So for an Euler-Euler model, so just steady state equations, steady state laminar flow, we'll say with negligible consumption. So that means the reactions aren't, there's no solid being consumed in any possible chemical reactions. Conservation of mass equations for both species, for both phases, and then conservation of momentum equations also for both phases. So most of the terms here are probably familiar to most people. Just to add things which may not be so familiar, well, the gravity term, I guess that's probably familiar to everybody. But then there's this interphase drag term between the solid and the gas, and that's given by some constitutive relation like this. This is known as the Ergun correlation, I believe. So I'm not sure if I have so the classical Ergun equation, where it's like we have a drag-like coefficient, which is very nonlinear in terms of being dependent. Well, here there is a difference in the phase velocities, but this also contains this epsilon s and epsilon g. So these are then the solid gas fractions, because the amount of solid and the amount of gas at each location, that will vary in space, and that's something we'll need to compute. We need a rate of strain tensor, so we're just going to assume that both phases can be taken to be Newtonian, so then that would be just given by that constitutive relation there. Some of the fractions has to be 1, and then this problem will need some boundary conditions. So to try to relate this back to what an operator in a blast furnace will be familiar with, so we'd specify the inflow rate of solid at the top, inflow rate of gas at the bottom at the 2 years, no normal flow and no normal slip at the furnace wall and the dead man, and then there'll be a solids flow outlet at the bottom. Okay, so then we have to try to solve this. So how do we do that? Remembering we're not going to do discrete element methods here, but just the continuous approach. Okay, so computational fluid dynamics. options that one could turn to, ANSYS Fluent, or if we had the patience to code anything up ourselves, we'd try with OpenFOAM. So that was the first thing that the PhD student in this project, who is the middle author there, tried. Yeah, and we really could not get this to work in any way. So although this kind of problem is this kind of gas-solid problem, it's well known, it's really more common in the case of fluidized bed problems. But here we thought that the issue was likely to be the fact that the top boundary, we want the top boundary to be both a solid inlet, but also a gas outlet. So we suspected that might be what's causing us the problems. Now, there are other people who do use CFD when using the potential flow model, but then we couldn't quite understand why you would use such a model anyway, so we didn't want to go that way. And then we just went back to our favorite asymptotic methods to try to understand what is going on here, so to try to do analysis and see if we could get something simpler. How can asymptotic methods be useful here? Well, we have to find some small or large parameter which can be the basis of the analysis. And for this, the obvious one, if one knows the problem or rather the process well, is actually the ratio of the solid velocity to the gas velocity. Because the gas residence time, that's known to be just of the order of a few seconds. But on the other hand, when you dump a piece of solid in the top, that will actually take a few hours to get you to the bottom. So yeah, so then the solid velocity is a lot smaller than the gas velocity. So then once we assume that, so then the original equations, they almost become too simple in a way. So instead of chasing all these nonlinear terms in the Navier-Stokes equations and so on, what we actually just get down to as the leading order balance is just between the pressure gradient and the gravity term. And then we also find that the pressure doesn't depend on the radius nor on the azimuthal angle theta. So in this version of events, and this seems justified based on the sizes of the parameters, the viscous and the inertia terms end up being negligible. And then it just tells you that the gas volume fraction and hence the solid volume fraction will only be a function of the vertical variable, which we're calling Z. And then once we have that result, well, then we can actually find what is the difference between we get an expression for the difference between the solid and the gas velocities in the vertical direction in terms of this gas fraction. So this result, I think people who do fluidized beds, they know that this is something called the minimum fluidization condition, by the by. And then, but then this gave us a way into the problem, but some simplifications that we did have to make were, well, as I mentioned, the gas inlets, they are actually, they are vertically oriented and the gas is coming in a horizontal direction, but then of course what it's doing is going up. So we replaced whatever the gas flow wanted to be there by some effective gas flow condition in the vertical direction at a height there, but the gas inlet height, that's very small compared to the overall geometry of the blast furnace. So we felt we were not losing too much there. Just to say, what are these curves here? So, well, this is the location of the profile of the blast furnace, and then that one is the location of the dead man. So that has the D subscript. Okay, so well, I've somehow done the non-dimensionalization and the simplified equation in the wrong way here, but okay, write out the non-dimensionalization formally, and then what we end up after some analysis is then that we end up with just a a quadratic polynomial out of all of this, just to find the vertical gas velocity as a function of the gas fraction. And so then that's eventually the polynomial that we'll get. It contains some dimensionless parameters, which then are given down here, and we use the numbers for this process to find whether these are large or small. So first of all, yeah, so just to plot the vertical gas velocity just as a function of the gas fraction, so that's solving this quadratic polynomial. So, well, that's the solution, and then we plug in the value of one of those dimensionless parameters, which ends up being large, and then that whole thing will just simplify to the vertical gas velocity being proportional or equal to, after non-dimensionalization, to the gas fraction to the half. And then to actually find the gas fraction, well, then we can go back to one of the, well, we can go back to the mass conservation equation for the gas, calculate both the vertical and the horizontal velocities of the gas. So that's essentially what's on this slide here. There's a few busy details, but what we'll end up with here, however, is then just a cubic polynomial for the gas fraction as a function of the vertical height. So cubic polynomials will either have one real root or three real roots, so we can do that test just to make sure that with these values we will only have one real root. And then what we end up with is actually that we find the gas fraction can be just found in terms of the profiles of the dead man and the profile of the shape of the blast furnace. So it's surprising it would actually that it would become this simple. So once you, in principle, know the shapes of those two, you could find what the gas distribution was. So then you, as a height of the vertical distance, and then you can plot that. This is just showing that last solution on the previous slide, comparing it with the solution of the polynomial, and then they for that value of the dimensionless parameter gamma, they're more or less on top of each other. Then we can finally backtrack to determine the solid velocity, and that goes back to the conservation equation for the solid phase. We work our way through there, and then we finally understand why people are modeling this as a potential flow, because you could, from this equation, you could define a new function, calling it the phi here, which is like the velocity potential we're normally familiar with. And then we can determine what the velocity will finally be. But the potential flow, it's actually not to do exactly with the solid velocity components. It's actually those solid velocity components times the solid fraction, which is then this 1 minus epsilon here. Okay, so then we can draw a few plots, and they qualitatively look okay. This is just this would be the example of the solid velocity along different vertical locations as a function of the horizontal distance. So this is at 3 different heights. So at this height, that would be like the full, at a location which involves the full width of the blast furnace. But then these curves, they don't go as far as that one, because now we're at different heights where the blast furnace width may be shorter. Okay, so this all seems to look very reasonable, and we got something out, and we published the paper, so thought we could be happy with that. But then one detail I didn't mention in all of this was when we were trying to determine the gas fraction epsilon, one step in there was, and which confused us, was did we actually use all of the boundary conditions that we said that we were using at the start. So I said we were going to need the boundary conditions at the top for the solid and the gas, and then also at the bottom. And in fact, we had used we just assumed that we knew what the gas fraction would be at the bottom, but then the model was calculating it what should be at the top, whereas actually, if we know how much solid we're putting in at the top, then that should be telling us how much gas fraction we have there as well. So we sort of got the reasonable looking answer, but for the wrong reasons. And in fact, if we try to break this model, it's quite easy to do. If we take the gas inflow at the bottom to be too high, the model will actually give us the gas fraction bigger than 1, which of course isn't possible. So there's still something wrong here. So actually, we didn't really understand the full story at this stage. And then we thought, well, we should maybe do this on something simpler, which would just be an analysis on a one-dimensional gas-solid flow. So then that's the one that's currently working its way through the revision process. So now we're just looking at the one-dimensional version of the Navier-Stokes equations, but for this Euler flow. So okay, so this then is containing the details that we were too scared to put in the first time. So I'm not going to go through all of the details because yeah, the algebra gets very long, but the maybe not so difficult. Well, let's just however dwell on the boundary conditions. So because this is then the important part. We can write down the ordinary differential equation, but in this problem, how many boundary conditions do we actually need? So we have to really count to make sure we have the right number. And the equations, although they're just one-dimensional, there's so many derivatives and variables, it's maybe not so clear how many we should have. So you might think we should prescribe the gas fraction at the bottom and the gas velocity at the bottom, solid fraction at the top, which will then give us the gas fraction at the top, but then also the gas or the solid velocity at the top. So then that's 4 conditions, and then we might think, well, at the top I really would have atmospheric pressure because the top of the furnace that is exposed to the atmosphere. So maybe we need that one. So looking at that we might think 5, but we know Navier-Stokes equations often you don't have the solution is unique up to a pressure. So maybe that last one wouldn't count. So then what we're trying to do from those, now it's 4 ODEs, trying to see can we actually rewrite them all just as one ODE in terms of one variable. And so in the end, it's actually possible to do, and it's done on this slide, and it's a non-dimensional version. So that looks like a rather long ODE to get into. And then we can also see, boundary condition at the bottom and boundary condition at the top. So at this stage, we're pretty sure this is the right amount. And if we find this UZG, the gas fraction in the vertical direction, we'll be able to find all the other variables afterwards. So at this stage, we're probably sure what we're doing, but how many dimensionless parameters does this problem have? Well, I think there's about 5 there. We can find out what all their numerical values are. Some are large and some are small. Then the key ones, which are going to be later on, we're going to see is this one, this new here, which is actually then, it's the ratio of the phase velocities divided by the ratio of their viscosities. So even from this position, it's not entirely clear what's going on. We do have just one second-order ODE, but very non-linear, but with very many dimensionless variables. But then when we systematically work our way through, what we actually find is that out of all of this, we get a problem which has basically a core, a central region where the velocity is actually just a constant. So that will be this one in the middle here. But then at the bottom of the geometry, there's this very thin boundary layer given in terms of one of the dimensionless parameters, this delta. And at the top, there's another boundary layer, and that's of this width R. So most of the analysis for this 1 and 2 goes through in a fairly straightforward way, but this number 3, the one at the top, which was the one we had neglected in the first version of the model, that one has been missed out. So then we just rewrite the rescale for the equations at the top. So that simplifies the second order ODE there, simplifies slightly compared with what I had on the previous slide. But then we start to try to understand, so it's a nonlinear ODE, is this actually going to have solutions? Are they unique? And so on. So the dimensionless parameters which are still left, or is that new? I already mentioned. There's another one called CG, which is related to the gas flow at the bottom. And then we actually find that with that ODE, the picture becomes rather complicated. For some combinations of those parameters, you would actually not get a steady solution at all. And that may help to explain why, when we were first trying to do the CFD, nothing could ever work. But it's more complicated than this because we also found that those equations, there could be a combination of parameters nu and CG, where the solution has well, I'm going to say no singular point. I'll explain what singular is in a minute. And there are other combinations where it will have a singular point. So what do I mean by singular point here? When we get through the analysis, what we actually find is it will be difficult to, numerics alone wouldn't have given us this. In fact, the only evidence we found something was strange was we kept getting different answers without understanding why we were getting this. So what actually happens is that the equations will have a solution which has an infinite gradient somewhere in the middle. And then further analysis will show that once we get such an infinite gradient, now infinite gradient here in the vertical gas velocity, that will give us a solution which is not unique, and we're able to show that. So then just giving this to a numerical solver from the start would never be able to pick this out. It would just probably give solutions, but will give different solutions on different days of the week, maybe, or different numerical parameters, like maybe convergence criteria, for example, or even if you refine the mesh very much, you would not necessarily get mesh independence. So then this is just showing results for 3 different values of a parameter, which I'm not given the details of here, and 3 different possible solutions. Okay, so I think I can already round it up there. So here what we found was that this asymptotic analysis, it actually told us how thin the boundary layers should be, and then guided us on how we should refine the computational mesh to find the solutions correctly. We found, based on the size of the parameters, we needed more refinement at the top than at the bottom. So the boundary at the top was a lot thinner than the one at the bottom. There are steady state solutions that don't exist for all combinations of the dimensionless parameters that we reduce the model to. There'll be non-unique steady state solutions for some combinations. So that may explain what's going on. And then the future work, well, we really just scraped the surface of the actual blast furnace model, which, remember, I said was time dependent, with different materials being put in at different times. So that's what we'll try to get to next. Okay, thank you.
Questions? Oh, help me out. Michael, did you have a hint beforehand that the 1D analysis would lead you somewhere? Because it's quite a simplification in the problem that you had, right?
Oh, you mean to make it 1D?
Yeah.
Well, actually, yes. Oh, sorry. Yes, I should be to the person furthest at the back, I should keep this as close as possible. Yeah, well, what I didn't present here, and what is in the paper that's under review is, then we use this as giving us the solution to the overall problem. So we do actually, so the solutions I've given here, then they can be used for the central part of the flow, but the boundary layer solutions are still at the top and the bottom. So we can actually use this result for even when the shape of the, when we do have a real shape of a blast furnace. But I didn't give that, I didn't give the details here. But what we're still missing, and where some numerical expertise would be great, would be to actually do a version of this where we don't rely on the analysis, but then can numerics, just using the basic Euler model without all of this, can it be made to work? And we asked a few people who had, I don't know, I think both, maybe a combined total of 15, 20 years of ANSYS fluent experience. So they suggested some things, but didn't seem to work. So that's why we had to do this.
Okay.
Yeah.
Okay. Thank you. Thank you. Questions, Santiago?
Thanks, Michael. I found that thing of ANSYS or OpenFOAM not working there. It was strange. What happened?
Well, OpenFOAM we didn't use. For ANSYS, yeah, I think we tried. So certainly with ANSYS, there were various options. I either just use a steady state solver or try to use a transient solver to work your way to a steady state. Some people suggested to us that we should use these user-defined functions then at the top boundary, to just extend that slightly and put in mass and momentum source terms. I think we tried that. Now it could be that now we have the analysis and we realize how thin those boundary layers are. It could be that, yeah, what we might have needed is just a very fine mesh at the top, and maybe that would have helped. But certainly, if anyone wants to have a go at this with us again, that would be good.
Okay, thanks. Maybe we can work together.
Yeah.
We are working on topics very similar in pipes.
Yes.
With gas and solid.
Yeah.
So maybe we can do something together.
Yeah. Thank you. Yeah.
Oh, thank you. Let's thank Michael again. Thank you, Michael. Very good, very good. Working with Michael Winicki, and now he's in the Federal University of Federal University of São Carlos, but not in São Carlos. Como que sei? So he's going to talk about computational framework for modeling hydrodynamic effects on polymorphism and crystallization. So thank you for accepting the invitation, Milton. Please.
Hello. Hi, good afternoon, everyone. First of all, I'm really glad to be here. Thank you for the organizers. It's a really nice event, and I happy to be part of this workshop. I was here doing my master's and my PhD under supervision of Professor Poti and Michael Winnick. And then I spent some time doing my postdoc in the University of Limerick. And what I'm going to talk about today is around this project for mathematical modeling of crystallization. Specifically, I'm be touching some points, modeling and results that has been published last year in the SciM journal. That is the team that published this paper that I'm going to talk about. So it's myself, Kevin Duran, members of University of Limerick, and Michael Winnick. The particular thing about building this model is that we were concerned about gravity. So we thought of gravity now as something that you can play with, that you can change in your model. And so you want to look at the effects the gravity will have in the numerical results in your analysis as something usually you don't change, it's just a constant in your model. And we were able to change it because this project was co-founded by Varda Space Industries. And they do just that. We'll talk about this company briefly to understand the context of this project. So Varda Space Industries is a company based in the US. And what they do is they build these capsules over there. That's the 3D render, but they have actually done the real thing 4 or 5 times. And they build these capsules and they equip it with a lot of experimental apparatus, and they're able to perform some experiments in low Earth orbit. So they fly these capsules to space, and it keeps rotating around the Earth for a couple of weeks, conducting the experiments. And they bring the capsule back and they collect the results, and they have a few areas of interest. One of these areas is the pharmaceutical industry. And they want to understand if the low Earth orbit environment can be useful to produce some drugs that are different, that could be more efficient. There could be new drugs produced in this low Earth gravity, low Earth orbit, sorry. So to talk about this drug manufacturing, we should understand a little bit about polymorphism. So this polymorphism is known as this capacity of a certain substance to exist in more than one shape. So it's the same, exact same chemical composition, but it will solidify in a different solid structure. So the crystalline lattice will arrange itself differently. So the substance with the same composition will lead to different properties. In fact, when these companies in the pharma industry patent a new drug, they have to describe the crystalline form, the crystalline arrangement, because all the pharmaceutical properties will change if you change the crystalline arrangement. There are many companies interested in this application, but the idea of all of them is, can we use the low Earth gravity or the low Earth orbit, the reduced gravity, to create some new drugs? And on the modeling side, we want to understand, we want to build these models and explore the results and understand if that's something that we can actually expect to obtain. So what we will see here is when we try to elaborate a mathematical model from basic principles. So it should be a very simple model, but a simple working model that we can later build on like a computational framework. And we explain these steps. So the crystals that we will be using here, they appear in the system by some nucleation. So the nucleation event is when this crystal is just pops up in the solution. And there are two big branches here for how you create your crystals. One is by primary nucleation, the other is secondary nucleation. But we will need these concepts later to understand what we are including in our modeling. So you have secondary nucleation when you are in this figure that's supposed to be a mixer, blades in a mixer. So as you are breaking larger crystals, you will eliminate the larger one and create a number of smaller crystals. So that's one way to create more crystals. And the other way is by primary nucleation. So you are actually generating new crystals here on this side that can appear on the system anywhere. That's homogeneous nucleation. Or you could have the crystals attached to some surface. That could be an impurity in your solution, or it could be the vial walls, or the blades, or anywhere else that crystal could attach itself to. So this in secondary, you actually need crystals already present, so you'll be able to break them apart. And in the primary, you can actually get it from just the solution. With 0 crystal, you get some crystals to appear there. And what's driving this appearance of crystal is the supersaturation. You will notice it in this arrow. We mean to say that the saturation has to be larger for the homogeneous primary nucleation. And actually for the secondary nucleation, you don't actually need supersaturation. You just break in crystals. So you can increase number of crystals, produce more by just breaking larger ones. But in our work, we will be focusing on primary nucleation, because even in the experiments when you're just breaking those crystals, you can start with some population of crystals, and that will be called seeds. They put some crystals already there to create more, but even in that case, that seeds must come from somewhere. So you must, at some point in your crystallization procedure, use this primary nucleation. We will be focusing on this side of the nucleation mechanisms. So we know that supersaturation is what's driving the nucleation, especially the homogeneous primary nucleation. And the supersaturation is, the supersaturation happens when you have in your solution some solute concentration that is larger than the equilibrium concentration. And how can you achieve that? In crystallization, they achieve that by either cooling the mixture or adding anti-solvent to that crystallization process. So let's focus on the figure on the left. In this case, we see here one substance with 2 polymorphs, A and B. So the substance with the lower solubility here in blue has the higher stability. So the form with the lower solubility is usually regarded as the stable polymorph. And the one on the top with the higher solubility level is the form B in this case, and usually referred to as the meta-stable polymorph. In this example, you see solubility changing with temperature. So as you increase temperature, you increase solubility. There is that easy example to understand this, like when you want to dissolve sugar in a liquid. Let's say you're putting sugar in your coffee or tea. If the liquid is hot, you will be able to dissolve that in a more amount of solute. So when you suddenly cool down that mixture, it will suddenly be able to hold less or inferior amount of solute. And that at that moment, you have some supersaturation. And the other way to create this supersaturation is by adding anti-solvent. So in this anti-solvent crystallization, you can start from one solvent, a really good solvent in which you can dissolve a lot of solute. And then you will add another second solvent to that mixture. And that solvent has much lower solubility levels to that solute. And when you add that bad solvent is called the anti-solvent. When you add that to the mixture, you drop the solubility level, creating supersaturation. So now we can just narrow down the modeling scenario to say that we will be talking about primary nucleation, homogeneous or heterogeneous. We will use the unseeded scenario, so there are no crystals to begin with. It's anti-solvent crystallization, and it is batch crystallization, meaning that we will be talking about crystallizing in a small vial, for example. And then we can start looking at the equations. So the most used equation when you want to model this population of crystals, in this case, is the population balance equation. So it has a couple of elements here. Let's start with the rate of change of crystal population. So we have a population density, N, and we have a population for each of the forms in the system. We have the transport. So we have population flux that could be around external spatial coordinates. So in this first term here, the second term, the population flux around external spatial coordinates, we are talking about transporting the crystal along X, Y, and Z. So the crystal is actually moving around your vial. The other term for the population flux is the internal phase space. So there's another coordinate here, the internal coordinate, that will actually be concerning the size of the crystal itself. In that example, in this figure, we had 3 external coordinates and only 1 internal coordinates. That in that case could be, for example, the diameter or the radius of a crystal that is assumed to be spherical. And when you transport the crystal, the population along that internal phase, you are having a growth or the crystal is either growing or shrinking in size. The other terms are death and birth of crystals. And that example over there is about collisions. So that's actually how you get the secondary nucleation. You break crystals apart, either by colliding with the blades, with the walls of the vial, or colliding crystals against each other. But in this case, building the minimal working model, we will neglect the flux around external spatial coordinates and the secondary nucleation. So our equation will be simplified to that. So we have a rate of change population density, and we have growth, which is, in our literature review, some advance in terms of modeling crystal populations for unseeded anti-solvent crystallization. And that's the results in population balance equation. We have a change in the population here of a certain crystal, a crystal form. This I means that we will be modeling 2 populations of crystals, the form A and form B. And we have the transport here along the internal coordinate, L, that is given by this population flux, the population itself, and the growth mechanism, the growth rate. So in this case, we are talking about a population density. So it's number of crystals per volume of liquid per characteristic length of the crystal. So that gives us a number per meter to the power of -4. And the boundary condition, the initial condition that we will have in this case, because we are talking about unseeded crystallization, is just 0. So we have no crystals to begin with, and that's where our unseeded crystallization gets into the modeling. If we were talking about seeds, then we just replace that 0 profile with some crystal distribution. Growth mechanism. So we saw that G term, that is a function of concentration, solute concentration, the characteristic length of the crystal, and time. So we are getting a growth mechanism that will depend on the crystal size itself, the concentration of the solute around it, and also change it with time. But there are different ways to build this growth mechanism. And there are two assumptions around this mechanism, which is for the crystal to grow, a molecule must first travel from the bulk solution towards the crystal surface, then attach itself to the surface of the crystal, be absorbed by the crystal lattice, integrated in the crystal lattice, and then that's when the growth is done. So it's a sequence of two steps that happen at the same time. But following the literature, and also to make this model simpler, let's, for this first time, just say that the rate of growth is diffusion limited. So we are saying that in this scenario, our growth mechanism would be proportional to the concentration or the solid concentration in the bulk minus the equilibrium concentration. So for each form, A or B, and we would have a different growth rate. Now we'll describe that mass transfer coefficient, K, a bit more carefully. And for that, we will use the Sherwood number. The Sherwood number is usually adopted in fluid flow and mass transfer coupled problems. And we can write that Sherwood in the mass transfer equation relation. So that is diffusion times Sherwood divided by characteristic length. So that's 2L, because in this case we are using radius. So the characteristic length of the crystal is the radius. If you are familiar with the Sherwood expression, you may have seen this without the 2, but it's just radius instead of diameter. And then, now that we are using the Sherwood number, we could use the Sherwood correlation, because there is semi-empirical correlations that can give you the Sherwood number depending on parameters. So you don't have to solve it explicitly. You can just replace it by these expressions. We took, well, from the main expressions in the literature, we took one recommended by these other two papers. That is actually a work that we did in a previous project, also as when I was working as a postdoc in Limerick. But we tested different correlations, and we saw this was appropriate one. And we see we can write the Sherwood using the Rayleigh number and the Schmidt number. So the Rayleigh number here, we taking into account the buoyancy effect, has the gravity term. So that's very convenient for us who want to include gravity. And then we can simplify the growth mechanism with the equation that we see here on the bottom. And we look at this equation and we see that the growth rate of a certain crystal will depend on the form of that crystal, if it's either species A or species B, because that will change the equilibrium concentration. It will depend on gravity, because gravity changes here with the Rayleigh number, and will also depend on the crystal size itself. So crystals will grow depending on its own size, species, and gravity in this model. Boundary conditions, right? It's the other part that we need to finish our modeling. So we include here the nucleation rate. At some point, let's say here L equals 0, we have a flux condition that can balance the flux of particles. So this nucleation rate is telling us how many crystals we are creating at certain time. And that nucleation rate, J, it comes from basic classical nucleation theory. So there has been some other authors who have improved this relation, but we aim to use the classical one at first. And this relation here, it ends up with nucleation rate for each of these crystal form, depending on the pre-exponential connect parameters and the supersaturation. So we see the supersaturation here as a ratio between the concentration of solute in the solution divided by equilibrium concentration. And that's okay, but one parameter that's really important here is this AI, the pre-exponential kinect parameter, because that parameter is usually fitted to experimental data. And this parameter, it will also determine if you are considering the primary, that primary homogeneous nucleation or the heterogeneous nucleation. So you change a parameter here, it will change how your model perceives that nucleation. If it's either just crystals attaching itself to impurities, or if it's homogeneous nucleation. But it's important parameter, and it can vary from something to the order of power of 10 to the power of 35. So it's something that can really change our numerical results. And so far, it's something that people can fit to experimental data. So there's quite a lot of change that can happen by fitting pre-exponential kinect term. The other equation missing is just the solute concentration. So that's an easy one because we start with no crystals at all, and all the crystals that we have at some point later, that mass must have come from the solution. So we must have extracted that solute from the solution to create the crystal that exists in a certain time. So maybe the only thing worth mentioning here is that we integrate, so we are adding crystals A and B, and we are calculating the mass of the crystals as if they were spheres. So it's 4/3 something radius power of 3. But we are including a volume shape factor. So we are using this volume shape factor to say how much the volume of a single crystal will differ from a perfect sphere. And that happens, that parameter there comes from crystallography studies. So experimental people will look at these crystals, in particular in their apparatus, and find the relation between shapes and sizes of crystals depending on their species. And that's, over there we have some examples of those crystals, that's experimental pictures. In this case, we are testing this model for L-histidine crystals. In that case, we had polymorphs A, which are rod-like stable forms, or polymorphs B, which are plate-like and metastable forms. So that's how they look like in real life. And that animation over there is just a representation of how we envision this model. So there is a population distribution here that, well, to begin with, is just 0. There are no seeds. Some nucleation event will happen at at some size 0, and that population will travel to the right, growing. So the growth mechanism is what makes this population move like a wave from left to right. So when we look at the model, when we look at the equation, we start to see some problems. And those problems, we have to overcome them to actually do some analysis. So the first one, easy to spot, is that the L in the denominator here suggests a degeneracy when that size comes to 0. And the way that we fix it was by doing a variable transformation. So we change that n by n hat, which is multiplied by L itself. And we non-dimensionalize, and we change that parameter L squared to a zeta to get easier to look at equations. And that's how it ends up looking like. So there are two important parameters there that we can just highlight, which is the term chi, which has the gravity effect on crystal growth. So it's the only term remaining, taking the gravity as an input, and the lambda term controlling nucleation. So these two terms we use later. Some results are not shown here, especially about lambda, but I would invite you all to have a look at the paper if you're interested. With that model, with that equation over there, we can do some analysis, which is not going to replace the numerical results or not going to get to the same extent of as the numerical results, but are usually important to look at. So one approach here is to expand that derivative, the z, and apply the method of characteristics. So we have that change in the population density. We obey that relation on the curves for z that look like that. And at this point, we don't have much insight of what's happening, but we could analyze this scenario where chi is much lower than 1. And in that case, we could simplify those equations for the change of the rate of change of population, which goes to 0. And this at dt, which becomes the concentration, non-dimensional concentration, sorry, minus the equilibrium concentration. So that will give us that the rate of change over here is 0, meaning that the population is constant. And that value, sorry, and that value remains to be determined, but we can think of it as, and well, we have the schematics of this characteristic here. I just have some water, sorry. All right, so what helps to get some insight about the behavior of this problem is we had the concentration in the solid over there. So that's the concentration in the solid, C. And with time, well, to begin with, the concentration is large. We have some supersaturation. We have the concentration of the equilibrium concentration of the metastable form. And down here, we have the equilibrium concentration of the stable form. So that concentration in the solid will drop. And after some time, it will reach the equilibrium for the metastable form. So in this region, you are creating, you may be nucleating and growing crystals B and A. But below this region here, this red dashed line, below that point, you will be dissolving crystals B. So you'll be dissolving the metastable form and converting that solid mass into form A. So when we look at the characteristics for form B, in here, on this axis, we have what happens at time equals 0. So that's the initial condition. And on this axis, we have the characteristic telling us what happens at zeta equals 0. So that's the boundary condition. We see that, well, we can sketch these characteristics showing that the crystals B will grow in the system up to some point TB, when the concentration in the solid reaches the equilibrium concentration for the form B. And then it will turn to the left. So the direction of these characteristics will shift from right to left, and you actually start to dissolve these crystals. And you get down to the point where you have dissolved all your crystals B. So from looking at these schematics that came from method of characteristics, you can expect that in your system, you will have both formation, crystals A and B, but at some point, the crystals B will start to dissolve in favor of more crystals A in the system. That's pretty much all the insights you can have from the method of characteristics. And the other approach, the numerical approach, is to take that system of equations and solve it. And the way we performed these numerical simulations was by using PyClaw. So PyClaw is the library, or is the Python version of ClawPack, the conservation laws package developed by Levesque. You can read a lot about it in Levesque's book about hyperbolic equations. So it uses finite volume methods, and it's designed to resolve these shocks that we see in the populations of crystals B and A. So it implies on using this Godunov type methods that's based on Riemann solvers, and with the addition of limiters. And in this case, we picked the MC limiter, the monotonized central limiter, that will help with these oscillations. So this was not the first attempt. We actually tried to solve it in commercial multiphysics software like Console. And the oscillations are a problem over there because it does not include methods like limiters or Godunov type that can handle that discontinuity. So the other option was to try to use ClawPack, and it was successful in giving a nice front for this shock without spurious oscillations and with some nice stability. And finally, we could use our model to look at the effects of many parameters on the crystal's number, size, and mass yield. And that's what our partners in the industry were interested on. Well, they are primarily focused on effects of gravity, but because we had all these other terms there, we could also check it and see how that could affect how many crystals you get, the size of those crystals, and the mass you are getting. The mass yield is the mass you are producing with your crystallization crystallization procedure. So this is one example of those results. I think yeah. So that's just to show that behavior of, we have here the solute concentration in the bulk that drops towards the equilibrium concentration of the metastable form. And then on this region, we are already dissolving crystals metastable. And then the concentration drops, reach closely to the concentration, the equilibrium concentration of the stable form. And we saw that population, that transient relation here for the population, that for crystals A, the crystals appear and move to the right, just growing, while crystals B, they start moving to the right, so this population appears in the system and grows in the system down up to the point where the equilibrium concentration here is higher than the solute concentration. Then you are dissolving crystals that are metastable. And then you can explore those relations in many different ways, measuring many different quantities. For example, I will show just a few examples of what you can measure here. One of those quantities is the theoretical yield. So these quantities come from talking with people on that crystallization industry, and the theoretical yield is pretends that you can extract all the possible mass of solute from your solution. That's the theoretical yield. And this fraction is how much, what is the fraction that I actually extracted from the system over time? So, and here I'm measuring it for different gravity levels. So that is microgravity, 10 to the power of -2, to hypergravity, which is 5 times Earth gravity. And at some point, this difference reaches up to 30%. So you can accelerate the crystallization of the stable form in hypergravity, and you can slow down that formation of the stable form in lower gravity. Other measure, other quantity that you usually look at is the most common crystal size with the most, with the largest population, the crystal with the largest population. What is its size? So would be the argmax of that population. And you can see how that changes when you change the initial supersaturation. And in that case, well, I don't know how much time I still have. Not much. Okay, so there's just a few interesting things that I'd like to just mention here about this plot, which is the size of the crystals are not increasing appreciably up to 1 minute mark. That means that, and that's one relation that is usually interesting, which is the balance between nucleation and growth. Because when you are crystallizing, you have these two competing mechanisms. If you want to remove solute from the solution, you can do that by creating new crystals or to grow crystals that already exist. And at the beginning, you are just creating more crystals instead of growing existing ones. But after some time, the crystals will grow and the nucleation will be negligible. This other test, just to mention, is mass fraction. So how the mass of the stable polymorph compares to the mass of all crystals involved. So is the mass of crystal A divided by the mass of crystal A plus B. In that case, it's just to hint towards an actual experiment in which these authors, they were crystallizing L-histidine. And they mention in their paper that when they increased the ethanol fraction in that anti-solvent crystallization, you increase ethanol fraction, they were getting only form B. So I know that they mentioned this in this paper, and it's curious because in our model, at some point, you get only form A. It may take a long time, but the relation that we make with this theoretical experiment is that in their case, they had such a high anti-solvent fraction that they could only get form B, the metastable one, and they didn't run the experiment long enough, and that could be true, for them to reach an information of the stable polymorph. So that's at least on the same direction that adding anti-solvent slows down the formation of stable form, but actually to get experimental validation, our model needs to grow a little bit, and we need to incorporate some of those factors that we've been neglecting. This last one is just a visual representation of the population density that feature in RTE Brainstorm. That's a local news, maybe not local, national in Ireland, that takes some column, a space in their journal to talk about scientific work. And for this piece of work, I took that population of crystal represented as rod-like shapes and plate-like shapes and place it on imaginary vials to look at how that would behave in the laboratory. So we compare 3 vials, one crystallized in microgravity, the other in hypergravity, the other on Earth. And we can see visually the proportion of crystals B to crystals A and how that changes with time. So at hypergravity, you are reaching a fraction of mass A much faster, or at least a little bit faster, than on microgravity. So microgravity is more prone to get the metastable form. Yeah. That's all.
Oh, very good, Milton. Questions? All right. So, nobody? You
There's one
Oh,
over there.
yeah. Oh, thank you.
Thank you, Milton. Have you tried central solver for the nonlinear advection problem, like Kurganov and more, or something like this?
Yeah. So in regards of testing different solvers, I tested different limiters, but I haven't tried many different ones. The first attempt was to use consumate physics. The other was to go back to Levesque book about hyperbolic equation and see what people could use. And he developed his own library, and then I was using it as in the full set of choices. There is hope to explore the numerical part of this problem, especially because we want to grow. We are only using here one dimension, the dimension L, but we would like to have bidimensional crystals. And to explore that, it's an idea that I'm writing proposals for that, so I could actually go into the numerics and test different methods and see what works better. And in this case here, in this project, we were working with the industry, so we had to get things, the one thing that worked to get results, and we did. But now, to have more fun with the numerical methods, it's another project that I hope to start.
Thank you. One more. How many species do you solve at the same time?
Yeah, so in this test, we chose L-histidine because it's friendly. It has two crystals, two forms.
Okay.
But there are substances of interest to the pharmaceutical industry, which has up to 14 or 15 species.
It is 14 differential equations solved at the same time?
Yes.
A system of 14?
That will be the case.
40 or 14?
14.
40.
Yes, yeah, that will be the case. So not necessarily that will be a problem with that. The model should work, but there's an increase in computational cost.
Okay, thank you.
Other question? You said something about the console doesn't have any special scheme to treat this convective term, right? So that is why you get problems with console, and then went to the PyClaw, and then you got stable things. And yeah, schemes like Kurganov-Tadmor are easily extendable to different to n-dimensional things, but the solvers that you are using based on Riemann solvers are not, right? So perhaps we have to investigate which solver would be best to take to console. Console has the possibility to implement your own scheme or not?
I don't think so. You can cooperate with, you can link it to MATLAB, but the way it actually solves the equation is kind of a black box. So it's not open in that way.
So if you want to investigate that, you have to take to like an open source.
Yeah, you have to shift to an open source approach. Sure.
Yeah, I see. Yeah, all right. Any more questions? So let's thank Milton again. Thank you.